There we go. Okay, welcome everybody. There's some new names and some old names, so welcome to students who don't know me, and for those that do, welcome back. My name is Rebecca Wegford, and I'm your online tutor for this module, or the second semester. The slides for this presentation or this tutorial have already been uploaded under the More Resources folder, so they are available there, and I will also upload the recording probably tomorrow once we've finished. So welcome. If anybody has any questions at any point, you're welcome to put them into the chat, and if they need to be answered during the course of this, I will answer them as we go. Otherwise, I will answer them at the end. I hope that will be useful. Sorry, I've got a little bit of COVID, so I'm just at the end of it, so I'm hoping I'm with you, and if I sound a little bit congested, I apologize. It's not my usual voice here. So this module is the thinking mind, and for the online tutor session, basically what we do is we cover what's in the textbook. I sort of summarize it for you to try and identify any areas where you might have difficulty. And it also follows what's on the online platform. On the online platform, there's lots of additional information. So please make sure you use the textbook and the online platform together in order to gain the most information that you can in order to guide you through. So this chapter on the thinking mind is our first dip into cognitive psychology. And it's broken down into 4 different themes, which are in the book and on the platform. The first theme is mental representation. The second theme is problem solving. The third theme is language and behavior. And the fourth theme is intelligence. So welcome to our first dip into cognitive psychology. I think it touches on each area quite superficially, and as you work your way through a psychology degree and into your honors, you go more in depth into each of these areas. So at this point, it's just the surface of what sits in cognitive psychology. So the learning unit outcomes, which means by the end of this unit, and this is as per your module guide, is the first one is standard, to define the key concepts in your own words, but thereafter we need to be able to explain the role of mental representations in thinking. We need to apply different approaches to concept formation to given concepts. We need to apply the 4 steps of problem solving to a given problem. That's your ICE task for this module. There is a problem, and you apply those steps to the problem solving. Please make sure when you look at that ICE task, it is broken into part A, and there is a part B to it as well. So just make sure you look at both parts to that task. We need to outline the roles of the relevant brain circuits in decision making. Outline the origin and building blocks of human language. Identify the brain structures involved in language participation. Briefly describe the contributions of different psychological perspectives in terms of explanations for language learning. Describe the various types of intelligence in terms of the available evidence for these, and discuss the roles of nature and nurture in intelligence. It sounds like a lot, but when you actually work through it, it's not that complex. It's quite straightforward. So let us start with the first theme, and the first theme is about mental representation. So that really talks about, with mental representation, what do we think about? We're talking about thinking, okay? And to think means to manipulate information internally. Remember, thinking is internal. It happens in our mind. It's how we deal with information that comes in and we process it. So by manipulating the information internally, we construct models of the world in our thinking about how the world is around us. It's about how we construct those models. We plan our interactions, so it's about planning. We regulate ourselves in terms of that information in order to reach our goals. So that's what thinking is about. And thinking in terms of cognitive psychology deals with things like perception, learning, memory, thinking, language, and intelligence. There's quite a lot of concepts in there that fall under thinking and cognitive psychology. So cognitions, when we think, the processes we use are information processing, we use thinking, we use reasoning, and we use problem solving. Those are our thought processes or the cognitions that we use when we are thinking. So to do that, we use symbols such as written language, hand signals, and we also use mental representations. So what form do thoughts take? They are visual in terms of how we symbolize them, but they're also internal in terms of how we visually represent them. So what is knowledge? When we talk about knowledge, knowledge is the entire body of information that we acquire through study, investigation, observation, and experience. So all of that knowledge comes in, and it's how do we process it using the different processes in our mind around thinking, reasoning, and problem solving. So that is what mental representation is. What do we actually think about? So mental representation, firstly, is thoughts as images. So that means thinking in pictures. It's about mental visualization. Sensory experiences that are stored in memory for future use that can be manipulated. So it's where we actually have a picture in our head. The picture at the top of the screen is chair or closet or table. We don't see that in words, we see that in images, as mental images. And we build on those mental images in our heads to develop concepts. So all of those different mental images come in, and we gradually take them and we build them from what we picture in our heads. We organize them in order to form concepts. So a concept is bigger than a visual representation. It's starting to extract from your experiences. It turns what you possibly think in your head as the picture of a dog, but based on our experiences, our concept of what a dog is grows and it changes. So it extracts that from our experiences, and we know that concepts need to be flexible. They can't be rigid. There's never going to be a rigid definition, because to a concept, there are always exceptions. If you, for example, have a dog and a dog has 4 legs and a tail, say the dog has lost a leg. Okay, that dog doesn't have 4 legs, it has 3, but it's still a dog. So there's exceptions to a rigid idea. They need to be flexible. And sometimes features overlap, they can be shared. But basically what we do is we put things in our mind into categories. And by forming categories, we can put things into those boxes, but a box is never completely sealed. The lines are always blurred and can be influenced by things such as culture. So if I say to you, for example, what do you think a dog looks like? Somebody who lives in a society where dogs are for security reasons, or you know, they might say, oh, a dog is big and it growls and it salivates and it drools and it barks, because you're thinking about the dog in the context of which you experience a dog. Somebody else might not have that experience. They might think of a dog as a puppy and something lovable and fluffy. So the categories of dog become blurred and they become influenced by our experiences, which also include our culture. So thoughts as visual representations basically start when children are young and they have got no experience of the world, and they see things as visual representation. But as we get older, as we experience things, those visual representations develop into concepts. I think a good example of a visual representation is when we do our mind mapping, for example. If you draw up a mind map of this chapter, you create a visual representation of what's in this chapter. And that's often why learning through doing mind maps and creating a visual representation is often effective for people. But the more you work with that visual representation, the more it will grow and the more concepts will be developed. So when we look at concepts, we have something called a prototype. That is your very, very basic entry-level point, okay, into a category. It's an average of all members of a category. So if you think about a dog, top left-hand picture is a very average dog, okay? It's got 4 legs, a tail, a nose. It's dog. Simple prototype, average members of all the categories. But then an exemplar is basically, it's a specific member of a category. So that could be your dog. When you think about your dog, you are now applying something that is built from the prototype and it becomes more specific. Both of them rest on similarity. So therefore, what happens when something is not similar to either? That is where the lines can be blurred, and sometimes you have to apply different thinking. So it's a tomato, a fruit. It's something we don't really think of as a fruit, but is it a fruit? It is. So it's not similar to the fruits we know. Okay, it's a specific member of the fruit family, but at the same time, we see it as different, but it is a member. So there are things that don't fit into the categories, and that's also what we have to be careful of. So when we approach concept formation, and this table is out of your book, there's a dictionary definition. That's a very straightforward, standard definition of what a dog is. There are common features. Okay, those are your overlapping or common features. Then you have your overlapping features where you can compare features of a suspected dog with the dog concept. You have your prototype, which is the average of all the members of the category, and your exemplar, which is a specific instance of a category. So that's when we think about things and we think about concept formation. Those are the different areas within concept formation we do need to think about: prototypes and exemplars. I hope you are all okay with this. Sorry. So concepts as theories. We look at concepts as theories. Theories are sets of facts and relationships between facts that can be used to explain or predict phenomena. That's very much what concepts are. Concepts are a set of facts and relationships between the facts in order to explain something. And we use concepts to guide how we think about it. And they don't exist in isolation. Everything around us impacts on how we think or perceive something to be. So concepts guide our thinking, but to understand that they don't exist in isolation. So we have prototypes, as we discussed, and we have exemplars, and that's a starting point. We start with those. And as we get new information coming in to our minds, through experience, through what we see and what we hear, we test that information against what we know, and we decide, does it fit into this category or does it fit into that category? But it's about taking facts and relationships and fitting them together. And often we get feedback from others in various ways to help us decide whether something fits into a particular concept or not. So concepts also can be like a schema, and a schemata represents the ways in which the characteristics of certain events or objects are recalled as determined by one's self-knowledge and cultural political background. For example, how you think about something, how you retrieve it from your memory, are very much bound by your environment, okay, your stereotypes and your worldviews. When you retrieve how you think of something, it is impacted by self-knowledge and cultural background, and it's a schema. So that shapes our memory storage and our retrieval, and it allows us to predict new things. That's the important thing about concepts, is it does allow us to predict. We take what we know and we think and we retrieve it from our memory and we think, okay, so what is going to happen now? Okay, a concept helps us predict new facts. So concepts in the brain, obviously within our brain we have different areas within our brain, and different brain activity correlates with different types of visual imagery. So an image of an animal, for example, if we see a picture of a zebra and its sight we're seeing, it's an activation in the visual cortex. So what we see, visual representation, it stimulates us in the visual cortex. If we're looking at something like the image of a screwdriver that is being used, we don't always see, if I say to you screwdriver, you don't just picture a screwdriver, you picture somebody using a screwdriver and screwing in a screw into a hinge or something. That is an activity or a movement, and so that is showing an activation in our frontal and parietal lobes. So how we see a concept, whether it's visual or whether we're thinking about it through thinking about a movement, different areas of the brain are activated. And I think always when we look at how the brain works, especially around thinking, most of the research is done through brain damage. And it's saying, how does somebody with a damaged brain react differently to various things? So therefore, when people have got brain damage in certain areas of their brain, that can obviously have an impact with visual images or concept formation and tasks. So overall, different ways of representing things and how we see things and how we think about things activates in different parts of our brain. So that is mental representation. And the interesting thing is if you look back, and it talks in your textbook about Temple Grandin, who is actually autistic, and she has developed a career in developing animal feeding processes, and her way of thinking is through visual representation. And she does a really interesting TED talk that once you sort of go through this section and you understand it, go back and see if you can find her TED talk where she talks about how she operates through visual representation, especially around autism, and it's a very interesting TED talk that you might enjoy watching. So that's the first section. It's about mental representation. How do these things actually appear in our brain, visually, mentally? How do we classify them, categorize them, sort them, and use them? That is what thinking is about mental representation. Is everyone okay with that section? So the second theme is problem solving. Okay, we did mental representation. Now we have problems. We all have problems. And I think this is a really good section And it's very relevant. It's nice to do this stuff because it's stuff we can actually every day, every minute, actually now interpret it and use it in our own lives. So what is a problem? A problem exists when the current state is separated from an ideal state by an obstacle. Sorry, Ali. Tell me, are you saying concepts can be a theory? What a theory is about knowledge and how things connect is how a concept works. So it's not saying that concepts can be a theory. It's saying a theory is information, relationships between pieces of information. The same thing applies to a concept. A concept is made up of pieces of information and relationships between pieces of information. So it's similar to a theory. Okay, it's like a concept could be a theory in our own heads as to how something works or why it's like that. It's a similarity between things. So we all know what a problem is, and I think we have all got problems at the moment, and it's where our current state is separated from an ideal state by an obstacle being the problem. So we get problems that are well-defined, and we get problems that are ill-defined. So a well-defined problem it's quite a straightforward problem. It means it's a solution that can be verified as correct or incorrect. Okay. Has the sun risen today? Or I don't know if the sun has risen today. Basically, it's easy. You go outside. Yes, it's risen. No, it hasn't risen. It's a very straightforward. It's a well-defined problem. A solution can be correct or incorrect. An ill-defined problem is basically got a more subjective solution. It's not always a clear problem. It's not a right or wrong answer. It's not a yes or no answer. It requires some thinking. And it's not necessarily because the problem is worded badly. It's just, it's not a clearly defined problem. It's called an ill-defined problem. And there is always that element of subjectivity to it as to how we think about it. So what problem solving does is it takes all the information that we need, and it uses that information to meet that goal, to overcome the problem. So there are strategies for problem solving, and I think we all have different strategies, and there are so many strategies available, but they all really hinge around the same thing. And problem solving takes effort. Ill-defined problems usually require more effort and thought than a well-defined problem. Sometimes we have to stop and think a lot harder about something, the more complex the problem is. So problem solving is never really linear. It doesn't always go in a straight line. Generally, the process of problem solving is looping. It means retracing some of the steps until we find a selectable, acceptable solution. So we have to understand that with problem solving, that it is generally a cycle that does require an amount of reflection and subjectivity. And so generally, in most ill-defined problems, we have to accept that the steps we have to follow and the steps generally are circular. So the example they use, or the process of problem solving they use in this particular book, is called Polya's problem solving cycle. So like we said, it's a cyclical process. The approach being, firstly, at the top, to understand the problem. Secondly, devise a plan. Thirdly, carry out the plan. And then finally, look back. That's the reflection, the part of it where if the problem hasn't been solved, we go back into the cycle again, or we repeat parts of the cycle. So it's understanding that the problem solving has to generally, especially in ill-defined problems, be a circular process with an element of looking back and reflecting and saying, did that work? Do I need to try something different? So that is the problem solving cycle that is used in this case. So step one in understanding the problem, and you apply this every day in your life. So this shouldn't be new concepts to you. It's just possibly putting it in a clear format, is understanding the problem. If we don't understand the problem, we're never going to find the solution. So in order to understand the problem is we need to collect, okay, data or the information, as much information as we can about the problem. We organize it in our minds or on a piece of paper, and we analyze it. The picture on the right says if you define the problem correctly, you almost have the solution, which is very true. If you spend time thinking about the problem, collecting all the information that you need, you should ultimately be giving yourself the solution. So the better you understand the problem, the more chance you've got of your solution being the correct solution. When we look at the problem, we also frame it in a useful way. So the mental representations we form in our heads relate to how we see the problem. Different representations lead to different solutions. We all might see a problem in a different way. We're not always all going to see it in the same way. We frame the problem ourselves. What might be a problem for us might not necessarily be a problem for somebody else. It's about how we framed it based upon what we know. But the first step and the most important step is to understand that problem. So helpful suggestions when you look at a problem. If it's a big problem, I think we've got a lot of big problems at the moment. Sometimes you break it down into smaller problem solving steps or sequential steps of smaller problems. So that often makes the journey easier. Don't always strive to reach the answer to the problem. If it's a big problem right up front, break it down into smaller steps. Personal biases can interfere with problem solving. It's really important you understand when you're looking at a problem that you are framing it based upon your own experiences. So to understand that however we see a problem, there's always going to be an element of personal biases in there. Your self-efficacy or belief in yourself may influence your approach to the problem. You might think, oh, this problem is too big, I'm never going to solve it. Or it's not my fault that the scale reads 100 kilograms, the scale must be broken. You know, it's not my fault that I weigh 100 kilograms, the scale is broken. So it's about self-efficacy, or the belief in yourself can influence how you think about the problem. And we also become very fixed in certain ways. So a functional fixedness is thinking about a problem in its most typical form. It can actually, by doing that, it makes our thinking quite rigid when we see that we're fixated on, I need to solve this problem this way because is this the traditional way? Sometimes we need to look beyond that. So when we understand the problem, when we look to understand the problem, be aware of those different elements in how we perceive the problem. The second step is to make a plan. So we've got all of the information we need. The next step is to make a plan. That means generating solutions to the problem and finding the best one to implement. So an algorithm, very straightforward, is a set of step-by-step rules that will help solve a problem. It's easier for a computer to do that, but it takes time and is taxing on the brain. So that's like a maths problem. Simple equation, it's an algorithm, you apply it, problem solved, done. As people, we tend to take a shortcut to problem solving. We use something called heuristics. Heuristics are very interesting. And that basically means it's a rule of thumb. It's a faster process, it requires less information than algorithms, but doesn't guarantee a solution, and it can lead us in the wrong direction and produce faulty decisions. So heuristics is a sort of, it's a way in our mind of short-circuiting a problem using a rule of thumb, but it can lead to the wrong decisions. So some people who write a lot about heuristics is Tversky and Kahneman, and they've got a really good book called Thinking Fast and Thinking Slow, which really sort of poses these kind of questions to the process of thinking. So instead of, it means that decision-making can be based on heuristics, which is our rule of thumb. But although that is not as taxing on our brain, so I think we're just going really with what we think of first, it can lead to errors and problems. So examples in the book that they give of heuristics is the availability heuristic. So think of something The example they give there is something that comes to mind easily when we think of as more common and important. So if you're trying to solve a problem, it's the first thing that is available to come into your head. What's easy to recall? So if we think about plane crashes, a plane crash is easy to recall because that's really what's it. So when we think about plane crash, we picture in our head a plane crash. We don't actually think about, well, for every plane that's crashed, there are hundreds and thousands of safe flights. So thinking about the plane crash first can lead to a fear of flying. It's called the availability heuristic. If we're talking about the cold, easy to respond, it's cold because last weekend was freezing. So we're all thinking about cold, but we don't think about, well, we're cold at this moment. Let's think about gradual warming, and we're ignoring climate change. It's sort of gone out of our heads. We're not thinking about it because the first thing we're thinking about is the fact that it's cold. It's what's available to us immediately, the availability heuristic. And that can be used at the expense of things that may be more common but don't easily come to mind. So when we are thinking about problem solving, be aware that often we think of things that are common without actually slowing down and actually thinking about the correct solution that's probably harder to recall. Another error in heuristics or biases is the representative heuristic. And that means that it's the likelihood of an event is evaluated by the degree to which it's representative of the major characteristics or the process of the population from which it originated. So experimental demonstrations that they use, judging professions from a brief character description. Okay, so think of a librarian. You have got something in your head of what a typical representative librarian looks like. And you see somebody who looks completely different, who you find out is a librarian, but they don't fit the picture of what you had in your head as being representative. So it's really important to understand that often in our heads, we take what we see as representative and we apply it across everybody without actually thinking that people can fall outside of that representation. So those are issues when we think about rule of thumbs and we think about shortcuts to problem solving. These are thinking processes that can actually impact on us making the wrong decision. If you have a headache but then you hit your foot and because you are distracted by the pain in the foot, no, it's not. It's something like, if you have a headache, the first thing you think about as to why you've got a headache could be the fact that maybe you had someone close to you who had a brain tumor. The first thing that comes to mind is, I've got a brain tumor, without actually thinking the likelihood of me having a brain tumor is 1 in a million, therefore the headache is not due to the brain tumor. So that is to do with the availability. It's what comes to your mind first to look when you're thinking about, why do I have a headache? Okay. The recognition heuristic is quite an effective one. It's making a choice amongst a set of alternatives by placing higher value on the alternative that you recognize. Okay, so when you recognize something, and it fits, it generally means it's more effective. So when we generate all of these solutions that we have generated to our problem, how do we know which solution to try first? There's never a set way of knowing which solution to try first. And again, our thinking processes are guided on so many levels. The effect heuristic means that we use our emotional response to guide decisions. So when we've got all of our solutions, what's our gut telling us? Our gut tells us that's the right solution, and it's based on possibly a similar experience with the problems. So we've generated our solution. You say, my gut tells me to go with that one. That's the effect heuristic. It's an emotional response. The utility theory, that is another process for selecting a solution. That basically means it's a little bit like a cost-benefit analysis of it. So you look at all the different outcomes, you weigh up the positive and the negatives, and you decide which would be the best one. That generally, obviously, takes a bit more time and a bit more analysis, but generally the utility theory and slowing it down, looking at positive and negatives, weighing up the options is probably one of the most effective ways for determining solutions to problems. And again, framing, how solutions are framed. Solutions chosen based upon willingness to accept risky solutions. So it's how do we look at it? If I do this particular thing, 5 people might die. But if I do this particular thing, 10 people might be saved. So what is more risky, having people die or saving people? So how solutions are framed. So it depends on your willingness to accept a risky solution. So when we try to think about solving or selecting our solutions, there are also thinking processes that come into play. No one is correct. They are all options, and there are others as well. But when we generate our solutions, these are the kinds of thinking patterns that we follow. Then our third step, probably the easiest step. Effect heuristic definitely is like your intuition, Karen. It's your gut response. Often we go with our guts, and often it's correct. So it's a very emotional response. It's your intuition. The third step is carrying out the plan. Obviously, that is your planning, your time, your resources. How am I going to do it? How long is it going to take? What am I going to need to do it? And the final step is the important part. It's the reflection part. It's looking back. Did making this decision, solving the problem this way, bring me closer to that goal? How do we measure? So when we look back, we need to also think to ourselves, what is the measurement to know how successful we've been? My problem was I was short of money to feed children in my creche because of COVID. We had no food. What are my solutions? How can I get food for my creche to feed the children? If I get 10 kilograms of porridge, then I'm going to be successful. Did I get 10 kilograms of porridge? And evaluation, always evaluate. Evaluation needs to be ongoing. Continually reflect back on the solution you chose. Is it effective? Do I need to change it? Was it successful or not successful? So that is the problem-solving cycle. There are many types of problem-solving cycles, but they all generally follow the same process. But each step, there are different ways in which we can think about it. So that is problem solving. And that if you haven't done your ICE task, basically there's a presentation of a problem. You have to generate different solutions and implement the problem solving cycle to that. I don't know what the trolley problem is. Sorry, Charmaine. I don't know if I've missed something, but I'm not 100% sure of the trolley problem. If you want to elaborate a little bit more on your message, I'm happy to come back to it. But framing is really how we see it in our heads and what is how are we perceiving it. You can look at something, frame it in a good way or frame it in a bad way. There are a number of ways to frame things in our heads. So with decision making, again, there obviously are impacts on your brain and the biological processes in our brain. And again, that's also assessed through brain damage and things that impact the brain. We've seen the responses in people's decision making. Some people make decisions quickly, some people make decisions slowly. Okay, the trolley problem, please, I'd love to know more. So if you've got a bit more time, just type it up, or you can just message me or email me what the trolley problem is, and I can definitely look at it. So in our brain obviously making all of these decisions. There's different representations of things, visual, all sorts of things happening. So there are 3 major brain circuits. You can send a link. Thank you very much. There are 3 major brain circuits in decision making. The first brain circuit really looks along the lines of pleasure and pain. That affects those different areas of the brain, or those are the areas of the brain that come into effect: the orbital frontal cortex, the ventromedial prefrontal cortex, and really these are just names at this point, the nucleus accumbens and the amygdala. I never know how to say that. I hate that word. It's a nice word, but I don't like saying it. So that is one of the brain circuitry areas. The second brain circuit area is around impulse control and unwanted responses. So we all know that often our brain or our thinking processes are affected by impulse or unwanted responses. Those come from the lateral prefrontal cortex and the parietal cortex. So when we look at impulse control, there's a thing called the value circuit, which arises out of that. As we get older and we mature, we're exposed to more social rules. So therefore, our impulses are more controlled as we get older. When you're younger, you have very little impulse control. You tend to do things irrationally. Again, that's part of development, especially in teenagers. But as we get older and wiser, we have a set of values, or a value circuit arises from that. So there's a brain area that's stimulated through impulse control. And there's also the monitoring of significant stimuli and more complex decision making or social decision making. That's a different brain circuitry, and that uses the insular and the anterior cingulate cortex. So as people get older, obviously your exposure to things changes. So there's developmental changes in your brain that impacts on these different circuits. And again, think back, we did a good in our exam, we did about taking drugs and psychedelic drugs and things, and you can see that there's different circuitry in your brain that are influenced through the taking of drugs. So if you take drugs, your impulse control is lowered. It's working in that area of your brain. Your decision making is based around unwanted responses or along pleasure. That's a different neurocircuitry. So there's 3 different brain circuits involved in the biology of decision making. The third theme is language, and how does language influence behavior? And again, this just touches on language. Language is very complex, and there's a lot of theory around language and development, and we'll touch more around language and development in further chapters, especially around developmental psychology. But basically, language, as we know, is a system for communicating, and we communicate thoughts and feelings, and it can be in many ways. It's not always spoken. It can be through sounds, gestures, and writing. Many ways language or communication takes place. And what language does, it allows for more abstract concepts beyond what can just be visualized. Language opens up a richness to what we think about and how we see things. So it allows for the development of things to become more abstract. Language connects people to others. So as much as I am with you here and now, there are people who we connect to by email, who are continents away. So language is about connection, and language also reflects and shapes our thought patterns. So again, that's to do with vocabulary, and the more vocabulary we gain, the more our shapes and it reflects the shape and shapes our thought. Sorry, that's supposed to be thought, not thou. Again, a rich vocabulary aids in thinking about a topic. So I mean, that's why reading is so important. The more we read, the richer our vocabulary becomes. How we develop words, for example, gender-free words, reduces gender discrimination. So there's so much power in language. It's a very important part of development and cognitive psychology. So the origins of human language obviously speaking is necessary for complex social behaviors, and language could have appeared with the first Homo sapiens 100 to 200,000 years ago, and it's even said the source of the first human language could have been in Africa. And so language is a living entity, and language grows with new words, but at the same time languages can also be lost. So as we are evolving, as populations are growing, languages can grow, but again, languages can be lost. If you say the universal language is sort of English in that context, people maybe speak more English and they lose their own traditional native languages, is that languages, if they're not used, can become lost. So over time, since language first started, it's shaped and evolved as we've grown. So within language, it's speech. There are building blocks in language. And I think if anybody ever tries to do one of those TEFL courses teaching English in a foreign language, it really takes you deep into these ideas that your phonemes is your basic sounds, which is limited only by your human vocal features. So there's actually a phonetic alphabet, which basically says how you say certain letters, like k, k for cat. It's your phonemes, your basic speech sound that obviously your own voice box and voice lets you pronounce. And then the next part of your building block is it takes those phonemes and it makes them into morphemes, which are your sort of words that carry meaning, the smallest components of speech. And we use grammar to fit all of those together. And English contains approximately 100,000 morphemes that can be combined to produce words. So within language, your very basic element is that actual sound for a letter M for mat, and then combined together becomes mat. So language is about building blocks. And when you look at development with children and you look at how you go k, 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 you teach children to say those short little phonemes first, and then gradually they develop into words and more elaborate speech components. So again, with language, what is the neurological process with language? And we know that language is managed by the left hemisphere of the brain. And again, brain damage often gives us more information about those areas of the brain and language. So aphasia is a loss of ability to speak or understand language. That is as a direct result of damage to a part of the brain. There's an area in your brain called Broca's area, and that area is an important part for language formulation. So it affects you might be able to want to say the words, but it affects the production of the speech. So as much as you want to say the word cat and it's there in your brain, you are unable to say the word cat. So the damage to Broca's area, it means that even if someone has the motor ability to form the sounds, the way they do that is damaged. Okay, so they lose the ability to form and express language. So somebody who's damaged in the Wernicke's area of the brain, Wernicke aphasia, affects the comprehension of speech. So the speech people are talking, the speech is rapid and fluent and virtually meaningless. It would be quite garbled. So different areas of the brain process different pieces of language, and we can tell through people who damage those areas what the impact of that is. So the two areas it speaks about in the book is the Broca's area and Broca's aphasia, and Wernicke's area and Wernicke's aphasia. So it leads to the question is, are non-humans capable of real language? So the evolutionary perspective says they should be. When we look about how we have evolved for different things, and animals do communicate, but they don't necessarily communicate through language or speech. They communicate in different ways, through sound, through movement. When a lot of the research has obviously been done about the great apes being the most representative of Homo sapiens, and they also have different sizes between the right and the left hemisphere of their brain, which does correlate the same as us to language ability. So from a neuroimaging point of view, the great apes should be able to speak, but the experiments that have been carried out show that that is not the case. There are cases where apes have mastered language understanding, but not necessarily speech. So cues, they have been, through process of repeating certain actions, they can understand signals, and it's based mainly on verbal cues and signals. So as much as they can't speak, there is an element of understanding and a similarity to humans. So are non-humans capable of real language in terms of speech? No. But they can show some level of language understanding and acquisition. So how do we learn language? And again, what's really interesting with how we learn language, and it reflects back to children, and we cover this a little bit more in developmental psychology, is children learn, it is almost natural to learn language. It's not like reading and writing where people have to sit down and are given lessons on how to read or how to write. A typical child from birth exposed to language will learn language. You can see that. So how do we learn language? They say that children even start to understand some language even when they're prenatal or still inside the tummy. But basically between the ages of 6 to 12 months and the first year of the child's life, children do become more successful at perceiving differences between sounds. Initially, if they might recognize differences that are big differences between different languages, but gradually as they get older, in one language, they can perceive different sounds within their own language or the language that's being sensed that is spoken to them. And social interaction is really important. So language is two-way. Don't just speak at a child. Speak to the child. Speak to the child's face. It's not always one-sided. It's about conversation. By putting a child just in front of a television, they're not necessarily going to learn language through observing. They learn language through being part of a social interaction. So language is learned almost intrinsically. And one of the theorists, Chomsky, down in the bottom right-hand corner, his theory is that there is an instinctive ability to learn language, and that all humans are born with a language acquisition device, which is a structure in the brain that allows babies to absorb and understand the rules of language they're being exposed to. The brain is able to analyze the language and work out the system that the language uses. So the speed at which language acquisition takes place, it's phenomenal how quickly children develop that language capability has led to the theorizing of actually an inborn capacity for language acquisition. And language acquisition follows a common course. So the children all of a similar age sort of have a similar level of language. And as we get older, our languages become more complex because we develop as people, we read more, we have more social interaction. So our languages become quite different. But children within a certain age, their languages are quite similar because they don't have those life experiences yet to build their language. So language can be considered as being a sort of inborn ability. Language processing examples, there are different ways of processing language, and it really focuses in this point of some of those areas where it's interesting to look at language. Dyslexia, I think you probably should all know what dyslexia is, and it's about experiencing difficulties in reading, But despite having typical intelligence and exposure to adequate teaching methods, so no matter what you do, teaching-wise, the child or the sufferer will still suffer. The teaching can be the same as somebody without dyslexia. The teaching methods are perfectly adequate, but dyslexia is still there. Dyslexia is strongly influenced by genetic factors. There's differences in brain structure between children or adults with dyslexia. Children or adults with dyslexia have difficulty differentiating basic speech sounds, and generally it shows a greater activation in the Broca's area in speech production. So dyslexia it's a problem. It's neurobiological. It can be genetic. It can pass through families, and it's quite common. About 1 in 5 children suffer from dyslexia. So despite whatever teaching you might experience, that the teaching is good, the intelligence is perfect, dyslexia is a process and a problem with processing language. Multilingualism is another language area that's interesting, and a proficiency in at least 2 languages. I think as South Africans, we are all definitely multilingual. Bilingualism is 2 languages, and there's definite benefits. The more languages you speak, there are associated benefits. It looks at sort of better executive control in your thinking. Apparently being multilingual or bilingual can delay the onset of Alzheimer's, and it's also protection against cognitive decline. So again, it's stimulating your brain, stimulating areas of the brain, and being proficient in 2 languages, or at least 2 languages, definitely has advantages. And sign language. Sign language is a distinct language using space and movement instead of sound. It is an official language. And again, images show that areas of the brain used are the same as for spoken and written language. So different ways of processing language. Language is not all the same. People have problems processing language, and you can process multiple languages in different ways. Final section is intelligence. This really just touches on the surface of what intelligence is, theme 4. So intelligence, as defined, is an individual's ability to understand complex ideas, to adapt effectively to the environment, to learn from experience, to engage in various forms of reasoning, and to overcome obstacles. Intelligence is quite a big definition, and it comprises multiple factors to it. So it's not a straight number, and I think we'll see that in the explanation here. So back in the day when the first intelligence test was developed by, I think it was Alfred Binet in 1904, and it was in France, and he was asked to sort of measure intelligence of school children. A sort of number would be assigned to somebody's intelligence, and that was your IQ, or your intelligent quotient. But over the years, as intelligence has been studied, different intelligence scales have been adapted, and over time intelligence tests have become more reliable and more valid, and they incorporate new features. So again, intelligent testing has limits around your social, cultural, or environmental biases. So it's not how a question is phrased in one culture could have a very different implication in another culture. So a lot of work has been done around making sure that any kind of intelligence scale takes into account all of these different biases that could happen. So generally, the way the IQ score works is that everybody's sits in a curve. The middle section of the curve is the normal population within a certain range, and on either end are, and we'll just discuss it a bit later, is the people who sit as outliers to that normal curve. So with intelligence, some psychologists focus on general overall abilities, whereas others focus on particular types. So you see the definition of intelligence was very broad, and it doesn't just focus on one thing. I am clever because I can do my maths problem fast. I'm clever because I can paint a picture blindfolded. There are all different components to intelligence. So Spearman he distinguished what was called a general intelligence, sort of an overall intelligence, which was sort of G was the name given to it for general intelligence, and specific factors that apply to single tasks. So within general intelligence, there's a fluid intelligence. That means it's about pattern recognition, ability to think logically without any prior knowledge. That's an important part of it. It's not something that's learned. It's almost like understanding a problem from looking at a pattern. We see those patterns, those problem-solving patterns, and they say, can you see 7 animals in this picture? It's almost about pattern recognition and thinking logically without prior knowledge. Crystallized intelligence, on the other hand, requires specific learned knowledge. So that's where we learn the rules of something and we understand them and we can apply them, and it's crystallized. So if we look, example, at chess requires fluid pattern recognition and crystallized intelligence about learning the rules. So our general intelligence is made up not just of the ability to see something and immediately solve it or identify it. It also requires learned knowledge, and as a result, it remains more stable. So within intelligence, as we said, one of the theorists, Gardner, he proposed there are multiple independent types of intelligence, and that's very true. People have different types of intelligences. If you're good at maths, you might be better at art or English. That just goes back to school. You might be better at baking or understanding a recipe to bake a flop-proof cake compared to somebody else who can construct a cabinet made of offcuts from the local timber yard. There's different types of intelligence, multiple: visual, spatial, linguistic, interpersonal intelligence, intrapersonal intelligence, mathematical, musical, bodily intelligence, naturalistic intelligence. So Gardner proposed it's not just one intelligence, there are multiple types of intelligences. And Sternberg, similarly, he has a triarchic theory of intelligence. So he's got 3 different kinds of intelligence, that somebody can have all 3 or just one. Analytical intelligence, that's problem solving and computation. Practical intelligence, we often see that it's street smarts and common sense. And creative intelligence, imaginative and innovative and problem solving. So again, different types of intelligences, the triarchic theory. So all approaches to intelligence can be useful, and we assume that people do have separate strengths and abilities, which can either correlate strongly or weakly to support general or multiple intelligences. So never ever say that I'm not intelligent if you're being compared to somebody else doing something. There are different areas of intelligence, and each one has its own ways for measurement. And when you do things like career profiling and things like that, again, you focus in on those multiple different types of intelligences, and what suits one person and they're good at it definitely might not suit another person, and they probably are not very good at it. Social and emotional intelligence, very important. A different type of intelligence. It's separate from cognition and thinking, but at the same time, it can exert strong influences on academic as well as professional outcomes. So we have an intelligence, but the intelligence is impacted by all sorts of things around us. It can be impacted by things like parental goals. What are our own educational goals? What is our work ethic? How do we see ourselves? Can I do something? Am I good at something? How willing am I to accept negative feedback? The ability to correct my behavior. So our social and emotional intelligence is just as important, and our social and emotional intelligence has an impact on our cognitive abilities, personal and professional. Biological, again, we just touch on the biology, is It basically, the standard measures of intelligence correlates with brain volume, especially the thickness of the cerebral cortex. That's interesting. And research on associations between brain structure and brain activity shows intelligence. Basically, intelligent brains enjoy quick and efficient communication between areas of the brain along pathways. And intelligence also correlates with brain development and the thickening of the cerebral cortex. So as our cerebral cortex thickens, our intelligence increases. Therefore, brain activity exercises that can develop the thickening should, in theory, make us more intelligent. Genetics and intelligence, again, we go back to nature and nurture, always nature and nurture. Are we naturally clever, or are there things around us that impact on our intelligence? So 75% of the variance in intelligence observed in the population can be attributed to genetics, which is not the same as 75% of your intelligence is attributed to genetics. About 75% of the variance or the difference in intelligence across a population can be attributed to genetics. So many genes influence brain development, but none of those genes have been conclusively linked to IQ. There's lots of genes, each has a small impact, but no one gene can make you clever. There's no clever gene. A number of smaller genes that can have small impact, yes. And IQ scores have improved over the years, generally on average by 3 points. It's known as the Flynn Effect. And again, as we've grown as a population, environmental factors have changed, socioeconomic statuses have changed, that generally our IQ scores have improved, but there are still significant factors within our communities that do put people at risk for low IQ scores, and poverty is one of those. So within a nurture context, those environmental issues do have a role on intelligence. So the final slide, and we're nearly done, is basically there's your intelligence graph that basically shows a population on the normal intelligence scale. That's the Wechsler Adult Intelligence Scale. Generally, most of your population sits in that peak at the middle section of the graph, okay, if you look at an intelligence score. But on either side of that is a tail end. And people who sit to the left and people who sit to the right, a very, very, very small part of the population sit in either end. So on the left-hand side, that's where there's an extreme with a lower intelligence score, which is what they call, according to your DSM, which is your Diagnostic Statistical Manual, it's an intellectual development disorder, which basically shows diagnosed after showing deficits in intellectual functioning beginning in early childhood, accompanied by deficits in independent living skills, classified as mild, moderate, severe, depending on IQ score and level of adaptive functioning. So where there are people with intellectual development disorders, they sit to the tail end. A small fraction of a normal population sit to the left. In the same way, a very small fraction of the normal population, and we always talk about the normal population, sit to the right, which is where the higher level of intelligence is, where you talk about gifted and genius. So gifted students generally have high IQ scores, whereas genius combines high intelligence with creativity and achievement. So a normal population score around intelligence sits a bit like that bell curve. The majority of your population do sit somewhere in that middle section, but it can tail off. And when you do a test on somebody, if they measure to the extreme left, they could be classified as having an intellectual development disorder, or at the same time to the extreme right could be gifted or genius. Is there a link between ADHD pupils being highly intelligent? I think there's a lot of research around that, Yuchi. There's no one answer, and I think you could actually just do your own research and you could find out, because again, there are different answers to that question. Everybody, that is the end of this chapter. I'm sorry it was quite fast. There was a lot to cover, but as you know, thank you for that also interesting. Cool. If you have any questions, I'm available via email at any time. I generally respond as quickly as I can within 24 hours. Sometimes if I do not respond to you, it might just mean your email got lost. So just give me a nudge and I will respond. This is a really interesting section. I hope you enjoyed it. The next collab will be in 2 weeks, and it will be on developmental psychology. This was cognitive psychology. Just, yeah, take your time, read the chapter again. If you're not sure, any questions, just let me know. I will hang on here if any other questions. Otherwise, guys, have a wonderful evening, and I will see you in 2 weeks' time for the next collab. But as I said, please, a due date for the ICE task. Yes, there is. The way I work with my students is I don't set a due date for each specific ICE task. There will be one date when you need to have completed all 4 ICE tasks, purely because after we've done this collab, you might want to go back and do your ICE task. But again, I would please just say, keep up to date with your ICE tasks. Otherwise, they just become too much when you've got assignments and things. So when you do the module, do your ICE task. And I can also give you feedback that's relevant, which is important at that point, not 3 or 4 weeks down the line when the feedback is no longer relevant to you. Ingrid, I don't know if you've got a question. Do you want to type it in the chat?
I do. Can I talk it,
no.
please?
Oh, you can. Hi, Ingrid.
Hi, Rebecca. Thanks so much for an awesome session. I really enjoyed it and learned a lot. I was just looking at the calendar and I noticed that there's the collab goes tonight, and then there's the second one for the second learning unit, and the next one is learning unit 4. I was just wondering, learning unit 3.
No, that's probably my error.
Okay.
I tried to fit everything on this weekend, so thank you for pointing it out, and I will check.
Okay,
I wondered why I was finishing 2 weeks early. Let me fix it, and I'll do it over the next day or so. Thank you.
No stress, no stress. Thanks so much, Rebecca. Appreciate it.
It's a pleasure. Thank you. Okay, thanks everybody. I will upload the recording tomorrow, and I'm going to stop recording now.